Thank you everybody for joining us in this week that is very full of exoplanet talks. So if you're here skipping out on the Exoplanet Demographics Conference, thank you for your commitment to Exoplanet Solar System synergies. So we have Mark Marley and Vikki Meadows are both going to talk today about spectra of solar system planets. Is that right? I think that's right. So Mark, of course, is a research scientist at NASA Ames, and he works on brown dwarf and giant planet atmospheres. And Vikki is the director of the Virtual Planetary Laboratory at University of Washington. And so she's going to walk us through some of the smaller planets. So I think Mark is going to start us off with the giant planets.
Thank you, Laura. Hello, everyone. Let me get my screen up here. So indeed, one thing, Vikki and I were thinking of things to talk about in the synergy talks is just to go through sort of what's there in solar system spectra and what are some of the features of that. Of course, we can't cover all this in much depth in just an hour, but we'll kind of get the best overview of things that we individually think are important. And so I'll start with the gas giants. And you see them here, and of course, just the first thing you notice for all of them is how important the clouds are in what you see visually. And of course, that also translates into what we see in their spectra is the role of clouds. And this is a nice set of the views here. You see like Jupiter looking at the South Pole, it looks different than the equator. At Saturn, we're seeing this nice bright storm at 65 degrees north. And Uranus and Neptune, you can see Neptune's dark spot hiding up there on the top left. So when we think about solar system spectra, the nice thing about the solar system is, generally speaking, you can think of the solar component of the planetary spectra as being separated from the thermal emission from the planet itself. And there's important exceptions to that, which we're both going to talk about. But sort of the zeroth order in the solar system, you usually think is, okay, am I looking at reflected solar or am I looking at thermal emission? And sort of the handoff between the two happens somewhere usually, but again, Vikki will talk about exceptions, of 4 to 5 microns. Now, this is the only time you'll ever see me show solar system planets as being black bodies, because the most important key thing to know and always remember and hold close to your heart is planets are not black bodies and their spectra are not black bodies. And we'll talk more about that. So let's dive right in and start with the visible spectra of the planets. And this is a full disk geometric albedo of Jupiter, Saturn, Uranus, and Neptune, and Titan as a bonus in the middle, by Eric Karkashka. And this is pretty much the definitive visible full disk spectra for the giants. And the way he did this is he put the slit down in the sky for his spectrograph and let the planet drift across it, and then integrated the whole time to get a mean spectra of the planet as if there was a unresolved disk. And so what you see, and you divide out the incident solar flux, is that most of the features you see are produced by methane, gaseous methane in the atmosphere. So almost all of these absorption features are produced by methane. The continuum flux level, as I'll talk about more in a minute, is set by scattering predominantly from the clouds, the bright ammonia clouds at Jupiter and Saturn, and the deeper cloud deck for Uranus and Neptune. Jupiter and Saturn, and also Titan, of course, have a lot of photochemical hazes, and the long drop off from starting around 600 nanometers or so and going to the blue is caused by haze absorption. Uranus and Neptune have these deep cold hydrogen atmospheres, and for them in particular, Raman scattering plays a role, where incident photons from the sun come in, and they're not purely scattered. Some of the photons deposit some energy into the hydrogen molecule, and that ends up shifting the wavelength of the scattered light a little bit. And the result of that is when you divide out the solar spectrum, if there's sharp features in the solar spectra, you get what are called Raman ghosts, which are, you can see there for Uranus and Neptune. And there's some science you can do with those, but I won't talk about that. Finally, there are some subtle ammonia features in Jupiter's visible spectra that you can't even really see here on Eric's plots from the ammonia in the atmosphere. You really don't see anything else. There's no sign of water or any other major absorbers here in the optical. Now, the sad thing is there's no real comparable unresolved planet spectra for any of the other wavelength ranges. And this is something that Emily Martin at UC Santa Cruz noticed and has successfully booted up a project to obtain unresolved spectra of all the solar system planets. And I don't have time to say much about it, but she calls it the PEAS project, where she has a dedicated telescope and is going to be feeding planet images through an integrating sphere to get out unresolved images. And so we're looking forward to that, and that'll provide a lot more of this kind of data. But going back to the reflected light spectra, the key thing to remember is it's really all about scattering. If we had a cloudless atmosphere, the blue photons would come in and be more likely to be scattered, whereas redder photons, because Rayleigh scattering is not as efficient in the REV, drill down deeper where they're more likely to encounter important absorbers like methane, or in warmer exoplanets, water or sodium and potassium. And so the planets a cloudless planet would tend to be darker in the REV. If you put a cloud in that scatters well at high altitudes, then you have a flatter spectrum. And so if you just think about the planets in terms of whether or not there's a bright cloud, a lot of the difference between Uranus at the top and Jupiter at the bottom really just comes down to the fact that Jupiter has a nice bright cloud that we're seeing them as methane absorption features against. In Planetary, there's a way of a framework for thinking about this a little bit more quantitatively. We used to call it a Baines diagram, and we've transitioned to calling these photon attenuation plots. It was Kevin Baines sort of popularized the use of these. And we're plotting, just zooming in here on the left, the two-way optical depth in the atmosphere versus wavelength due to different opacity contributions. So for example, here, the dark black line is showing where in the atmosphere we're hitting a two-way optical depth for methane. The dotted lines on the left here are for Rayleigh scattering. And so if you're a photon coming down here on the left, say around 0.5 microns or so, you come out, you encounter the atmosphere, you drill down, and the first thing you encounter is Rayleigh scattering. So you can scatter back to space, and the planet looks bright from Rayleigh scattering. But if you're a little bit redder, you come down and don't quite get to that two-way optical depth 1 for Rayleigh scattering, but you do first encounter the absorption of methane. So maybe you're a little bit darker, and fewer of those photons get back. Whereas finally, if you come down and say 889 nanometers in the strongest optical methane band, you encounter the methane absorption way before Rayleigh scattering, and so very little of that light gets back. If you then insert a cloud deck high in the atmosphere, then you would hit that first, and all of these things would scatter back. You'd have a flatter spectrum. If the cloud's deeper, maybe the cloud's most important in the bluer wavelengths, but the red gets absorbed. And then if the cloud's too deep, then it's back to where we started. And this kind of trade-off, this wider spectrum trade-off between scattering and absorption, really is what sculpts all of these spectra in reflection, and a lot of what bread and butter planetary science is using these things to constrain the atmosphere. And as we look forward to the Nancy Grace Roman Space Telescope with its coronagraph, that's the same kind of science we'll be doing. Everyone will be doing in the optical with the CGI instrument. And these are just different models, the solar system giants, along with some a cloudless case or a 2AU Jupiter. As we heat up or cool down a planet, these top clouds will burn off and we'll see different cloud layers, and that'll produce a lot of interesting diversity. If you're interested in playing with these things, I'd encourage you to download Picasso, which is the geometric albedo tool, open source tool developed by Natasha Batala. And part of the output we have from that is these same photon attenuation plots. You can see what's controlling the spectrum as a function of wavelength. And so just to drive this home, the reflectivity depends, for example, on Jupiter, so inhomogeneous with where you are. And these are some nice figures from Dahl et al. That were presented at the DPS just this year, where they were looking at different spots on Jupiter. You can see that the different belts and zones in the figure on the top right. And if you take a spectrum of each of those, this is I over F, which is like albedo versus wavelength, you can see how much difference there is at some of these wavelengths just from the different color in the clouds. And so a whole disk, when we look at, you think of Jupiter as the whole disk planet, really is averaging over all of this. It would be, and then what's very exciting from Juno, from the south polar views from Juno, is how blue Jupiter's south pole is, which means to me there's a lot of more Rayleigh scattering from a deeper cloud deck. But unfortunately, Juno didn't carry a spectrometer with it, so we don't have something like this for Jupiter's south pole. So that's the optical. As we move into the near infrared, it's the same pattern of reflected light and these important absorbers. We pick up around 1.5, 1.6 microns ammonia now, so it's no longer just methane. And this reflected light goes all the way out again to about 4 microns or so. The bottom left are some images from the Shoemaker-Levy 9 impact onto Jupiter. And I remember at the time I was on the email exploder for everybody sharing their images. And these images were taken right here at this 2.3 micron methane band. So here in sort of the center bottom, where the planet is normally very dark. And I remember in the email chain, there was people saying, oh my gosh, Jupiter, but these impact sites must be so hot. They must be like 2000 degrees because they're glowing so bright in the near infrared. And of course, it wasn't that at all. It's because the impact deposited very high in the atmosphere, these fine particles that then scattered back photons. And so what you're seeing at the left really is an example of what Jupiter would look like if it had a high bright cloud. More generally, these are models for Jupiter, Saturn, Uranus, and Neptune. And again, showing it's the same pattern of clouds trading off with methane opacity all the way out to about 4.5, 5 microns. We're in the red here, I'm indicating we're starting to pick up the thermal emission. Then further out, beyond 6 microns, we are in the range of thermal emission. We start to see molecular features from methane, now in emission, I'll come back to that point, and ammonia, notably around 10 microns for Jupiter and Saturn. For Uranus and Neptune, they're so cold, the ammonia is all condensed out deeper in the atmosphere, so we don't see it. And instead, the pressure-induced opacity from hydrogen starts to be more important. Then beyond about 10, 12 microns, we start to pick up emission features from ethane and acetylene, which are photochemical products, not from equilibrium chemistry. And then finally, as we go longer and longer wavelengths, we kind of start to come up the black body curves for these planets, especially Uranus and Neptune, which are much colder. This is from ISO, a spectra of Jupiter. The top panel is the real observed spectra of Jupiter. The bottom panel is the model. And you can see there's the methane, there's also some phosphine, the ammonia, and then those disequilibrium species. Notably, and also CH3D, the deuterated methane. The methane, the acetylene, the ethane are in emission. And that's because there's a temperature inversion on Jupiter. And so we look at the temperature profile on the right. You can see Jupiter the temperature starts increasing above 100 millibars or so. And because those ethane and the methane at 7.8 are very strong, we're probing high in the atmosphere against a cooler background. And that's why those bands are in emission, not absorption. I want to go back though to sort of the main gold mine for Jupiter, which is the 5-micron region. And the region, a way you can tell that it's important is to look at this plot of molecular opacity as a function of wavelength. This was prepared by Richard Friedman. The black is water opacity, the red is methane opacity, and the green is carbon monoxide. This is just sort of the raw gas opacity. For Jupiter, the water is condensed out deep in the atmosphere. So you imagine sliding that water opacity much, much lower. It's not very important. Likewise, carbon monoxide is there only in trace amounts. So imagine sliding the carbon monoxide down off the plot or lower on the plot. And then what's left for controlling the opacity through here is methane. And you see this broad minimum from 4 to 5 microns in the methane opacity. So if you're an air parcel deep in Jupiter's atmosphere, sitting at 4 to 5 microns, you can start to radiate away to space much deeper than you could at other wavelengths. And so it's that emission from deep in the atmosphere that causes Jupiter's famous 5-micron hotspots, which is what we're seeing in the top image of Jupiter. When there's holes in the clouds, you can see deep. The brightness temperature is shown in this middle panel by Drossard et al. In 1998, where there's the spectrum of Jupiter and then black body curves. And so you can see these hotspots are like 170, 180 Kelvin, so much warmer than the normal Jupiter. And this is yet another example. Planets are not black bodies. Jupiter as a whole does not radiate at 170 Kelvin, but it does through here. And because you have this deep path length down through the atmosphere, you can start to pick up much rarer species. Like arsine, germane are important disequilibrium species. A lot of science has been done with those, and you can see down at the bottom around 4.7 microns, spectral features from both. And I've highlighted here in red the 5-micron spectral region. Gordy Bjorker has done a lot of work on this region. He's probably the world's expert on Jupiter at 5 microns. And here is a plot from one of his papers showing the observed Jupiter emission in the red dots, along with a lot of spectral features labeled. The S's are solar features, but you see phosphine, CH3D. But here at Jupiter, he's modeling this with just purely purely thermal emission. This is Jupiter radiating away to space and no solar reflected contribution. But if we go to Saturn now, the same kind of plot, but now we're looking at Saturn. Again, this is the 5-micron region plotted in wave numbers. Here we're at 65° north, relatively cloud-free spot, and he models it entirely with thermal emission. So the green line is the model, which lines up really well with the data points for Saturn. So here at this spot in Saturn, sort of following the rule of thumb that 5 microns, we're looking at thermal emission. We're seeing thermal emission. And again, these species we see because of the long path length, like phosphine. But same planet, go down to the equator. And now it's just the opposite. He finds the best fitting model is entirely reflected light. So a higher, thicker cloud model, something like 0.4, 0.5 bars, matches the data. So that rule of thumb is then wrong here, because some parts of Saturn we're seeing reflected light, some parts of Saturn we're seeing thermal emission. And this is just one example of that's not a hard and fast rule, but we're seeing in this transition wavelength region. So finally, it's kind of cool that, we always have had Jupiter, and we always think, okay, this is what Jupiter looks like. And one of the great things that has been so fun about brown dwarfs the last 20, 25 years is it allows us to see our own planets as being part of a family. And this is a great figure from Mike Cushing showing real observed data, except for the gray trace, the one gray trace. This is all real data for an M dwarf star at the top, then an L dwarf, brown dwarf around 1600 Kelvin, a T dwarf with a Y dwarf, and then Jupiter. And you can see that as you go to cooler and cooler temperatures, the molecular absorption bands get deeper. What starts out as CO for the M dwarf transitions down to methane for the T dwarf. And at 10 microns, we start to pick up ammonia and the methane fundamental. And so we're seeing all of these molecular features. We see the excess at 5 microns. And finally, we get down to Jupiter. And of course, Jupiter here, the shorter wavelengths is reflected light, not thermal emission, but it looks the same. It has that same feel to it from the molecular opacity being so important. And so really Jupiter is in family with the rest of its more massive cousins all the way up to the coolest stars. So from the lessons from the giants for the first half of the talk here, again, planets are not black bodies, and all of the richness comes from the molecular opacity varying so much with wavelength that allows you to look to different depths at different wavelengths. What we do see is consistently a trade-off of scattering, Rayleigh scattering, particle scattering, gas opacity, the temperature structure. The reflection and thermal emission are generally, but not always, different domains. And having this broad wavelength coverage is really crucial. And that's what legacy planetary science uses to constrain the cloud properties, the atmospheric abundances, the temperature profile. The photochemical disequilibrium species are important. And I'm really looking forward to when we eventually get cooler planets from direct imaging that are more like our own planets. And we can really continue to place our planets in context with the whole family of worlds, just like we did with brown dwarfs and Jupiter. So I'll stop there. Should we take questions now, or should we take questions at the end?
I was thinking maybe at the end for a general discussion, but I am open to either mode. Maybe I'll just rattle through.
All right. I'm sorry.
This is Jim Green. I was going to ask about what kind of spectral information do we have in the infrared on the dark side of Jupiter, the night side?
I tried to convince the Cassini folks to do deep integrations of the night side of Jupiter, so you could see if there's any thermal flux coming out in like JH and K. And I wasn't able to do that. And that's why you need to have, since you're Jim Green, I will make this point, you really need to have exoplanet people taking part of future planetary missions as guests somehow in the mission to think of these kind of observations and encourage the team to make exoplanet relevant observations.
Okay, the mistake was you didn't call the planetary division director and insist on it.
Yeah, I tried standing on Kevin Baines' foot, but it didn't help.
God, okay. Sorry, I wasn't there to help.
Want to go ahead, Vikki?
Oh yeah, okay, sure. Okay, so thank you, Mark, for that very calm and measured and well thought out presentation. So as I give my presentation, you'll probably determine that I have a little bit more of a chip on my shoulder than Mark has about all of this, so that will come out in this presentation. So I'm going to talk a little bit about the terrestrials. And I was just going to start out with some of the things that have motivated me to give this talk, which is that, over the years, this may be a well-kept secret, but I started out as a planetary astronomer. I'm a Venus scientist. And so during the course of doing my Venus science and getting on terrestrial planet finder working groups and whatever, I've heard a lot of things said about terrestrial planets. So these are some of the things, we can just approximate them as black bodies, which I hope Mark has totally convinced you that they don't look like that. Because the clouds we can't see to the surface of Venus, except in the radio, we can measure atmospheric pressure of a planet's atmosphere using Rayleigh scattering, or we can just measure the temperature of a planet or calculate its equilibrium temperature, and then we can determine whether or not it's habitable. And my absolute favorite one was when I was an observing run for Venus, and a cosmologist asked me across the lodge dinner table, does planetary science actually have any physics in it? Isn't it just pictures? So today I'm going to talk a little bit about, and of course this caused me to give people looks like this, but I'm going to talk a little bit about sort of the things that go on with the spectra of terrestrial planets and how, yes, there's lots of physics in it, and also just how diverse they are and how you really can't make sort of assumptions based on perhaps one example. So terrestrial planet spectra are impacted by and so can reveal a lot of things about a planet: the composition, the gas, aerosols, that's hazes and clouds, and the surface. So that's an additional thing we pick up over what Mark was talking about. We can, if we have spatial resolution, get at atmospheric pressure in various ways, and I'll talk a little bit about that. So there's Rayleigh scattering and line profiles that we could potentially go after. But I'll again point out that if you're trying to translate this to exoplanet science, where you're working more in the disk average, sometimes that translation won't work. And then surface and atmospheric temperature are things we can also go after via thermal radiation within atmospheric windows, which I'll talk about. We can look for things like temperature inversions, which can reveal the presence of a UV shield for the surface, which is important for us when we consider terrestrials. But again, the fact that we won't have spatial resolution on a lot of our planets is probably going to cause us to not be able to do this as comprehensively as we would like. And then, of course, there's phase and temporal variability that also can come from observing spectra over time. I'm not going to talk very much about that today, but that is definitely something that you can get out of these types of spectra. So let's just start with sort of a very broad overview of the terrestrials. So here's Venus, Earth, and Mars, appropriately color-coded. Just to give you an idea of what we're looking at through the visible sort of early near-infrared region. You can see that the spectra are quite diverse. If you look at Venus and Mars, you can see they're both dominated by CO2. But the narrowness of the bands in the Martian spectrum are a byproduct of the fact that you're really just seeing down to about 60 millibars of pressure. And the temperature factors into that as well. And so you're seeing sort of this very thin sort of almost exosphere of atmosphere there on Mars. For Venus, you have more, you have stronger CO2 bands. But throughout most of the visible region, actually, you're really only probing down to about 30 millibars on Venus, because the clouds and their large scattering capacity do in fact stop you from being able to see down into the lower atmosphere. Then for the Earth, we have probably the more complex spectrum there, where we have things like oxygen, which we don't see for the other atmospheric compositions, and water vapor that really dominates the spectrum of our planet overall. So these reflectance spectra can reveal a diversity of atmospheric compositions, aerosol compositions, surfaces, and atmospheric pressures. And I also want to point out, if you look down towards the short wavelength end of those spectra, you can see that this simplistic idea that, oh, we can just use Rayleigh scattering to figure out what the atmosphere is kind of gets clobbered by the fact that there's a bunch of stuff going on below 0.6 microns for pretty much all of these planets. For the Earth, even though we do see kind of a Rayleigh scattering tail here, we are also in a very large ozone absorption band that goes from 0.5 to 0.7 microns. For Venus, we have something called the unknown UV absorber, and that's exactly what we call it because we don't know what it is. It tends to cause the spectrum of Venus to sort of dive towards the UV, and again, because we're not seeing down deep into the atmosphere because of the clouds, we're again sampling a much less dense atmosphere than you would expect for Venus. And so again, we're not in reflectance able to get down in there. And then for Mars, we have very strong absorption from the surface of the planet itself, the iron oxides. And so there is a bunch of this sort of complexity going on down here, which makes it, a simplistic statement to say we can just measure the Rayleigh scattering and figure out what the pressure of the atmosphere is. So be aware that for terrestrial planets, you might have an underlying surface composition that's going to, modify what you think you're seeing. And again, there can be molecular absorption or, whatever the unknown UV absorber is that can modify that as well. So those aerosols, so clouds and hazes, can significantly change the spectra of planets. And this very messy diagram here, just follow the color pairs, are kind of showing the overall effect. So the Earth's water clouds, so here's without clouds and then with clouds. So clouds produce a higher reflectivity on our planet, which is actually not a bad thing if you're trying to detect things like oxygen, for example, because it essentially raises the continuum because of that reflectance. It raises the continuum up to the point where you can actually potentially measure a particular absorption feature more accurately, because the actual bottom of the band, which you would like to measure for abundance determinations, is actually at a higher reflectivity level, and so you can get better signal to noise on that. So clouds aren't always terrible for trying to characterize atmospheric composition. For Titan, we see the effect of the hazes here. You know, that once the hazes are seen and present, you get this drop off in brightness. And then for Venus, again, you can see this upper level here where you are getting essentially very weak CO2 signals, because again, you're probing above the clouds. But if we were to take the clouds away, you would see very deep, strong signals coming from Venus. Okay, so the clouds and hazes themselves can actually display strong features also. Again, this high reflectivity we get from Venus is thanks to its H2SO4 aerosol and clouds. Down here for Earth, we can get, this Rayleigh scattering from the atmosphere itself, but again, also the strong absorption from ozone that tends to sort of just truncate our Rayleigh scattering maybe a little too soon. And then for these other models, which are hydrocarbon haze, Archean type, early Earth type models and clear sky models, you can see the very strong effect of hydrocarbon haze would have on, for example, a terrestrial planet. Okay, so if we go now to thermal emission spectra for the terrestrial planets, we can see what is probably one of the biggest takeaways really about terrestrial planets is that the carbon dioxide band, and carbon dioxide in general, is one of the most detectable features in terrestrial planet spectra. So when we think about exoplanets and we think about trying to characterize an exoplanet as being more like the Earth than, say, mini Neptune, then CO2 is one of the things we will definitely want to go for, and CO2 will oblige us by being actually a very strong feature in terrestrial planet spectra. The interesting thing, though, is even though, for example, the CO2 on Mars, it's 96% of the atmosphere in a very thin atmosphere, but you still get, very strong features from this band. And it's one of the truisms that the CO2 is easy to detect, but it's actually difficult to use it to discriminate the abundance of CO2 in the atmosphere. So you know it's there, but it's a bit difficult to tell how much of it is actually there. So other features, we have, strong carbon dioxide hot bands that go through this region here for Venus. We have sulfur dioxide features in here as well. For the Earth, there's methane and sometimes N2O down in this particular region that can be seen. And then, for Mars, again, a lot of CO2 features. And then over here in the sort of long wavelength end, even small parts of water vapor, 1 part per million or so in the Venus atmosphere can affect the very long thermal tail. But for Earth, there's a characteristically strong absorption of 6.3 microns from water vapor. Okay, so let's talk a little bit about what we can get from the thermal data. And I just want to point out too that early on, especially in exoplanet science, there was a tendency to just use the equilibrium temperature for everything, and dangerously assume that we actually knew something about the planet's environment from that equilibrium temperature. So the point is, though, that if you look at the equilibrium emitting temperature, so the temperature we see in the continuum for a lot of these planets, you'll get the values over here on the left-hand side. So for Venus, you're 260 Kelvin, which sounds pretty cold for Venus, but again, you're emitting from above the cloud layer, essentially. About 300 Kelvin for Earth, 275 for Mars from these spectra. But the actual average surface temperature over the disk for all of these objects is, 743 for Venus, 288 for Earth, and 223 Kelvin for Mars. So again, part of this is affected by the fact that these spectra were taken over spatially localized regions. And so for Mars, for example, you're seeing a particularly hot part of the planetary atmosphere and surface rather than the disk average. But again, in the case of Venus, because we're not able to penetrate down through the clouds at those at these wavelengths, but we're seeing the emission at these wavelengths, then in fact you get a much cooler temperature from that observation. So if we go to the Earth again and look at this in a little bit more detail, another interesting thing about those spectra, and I didn't point it out on the examples previously. In fact, I can yeah, just do that very quickly. One thing also you'll notice about the CO2 band is it looks different for these different planets. So the CO2 for Venus and for Mars has a characteristic U shape, which tells us that we're not looking at a thermal inversion in the upper atmosphere. But the CO2 band for the Earth is in fact a W shape, which shows the inversion at the center of the core of the band. So that's what you're seeing here is this W shape from CO2. And that gives away the fact that our temperature pressure profile is in fact increasing with altitude up in the stratosphere. And that signal is seen in here. Basically in the wings of the band where there isn't a lot of opacity, you're able to penetrate more deeply into the atmosphere, or in the case of emission, basically see photons released from deeper in the atmosphere. They're able to escape out because the opacity is lower. And so down here at the edge of the band, you're essentially probing the surface. As you go down the side of this band, you're getting more and more opacity, and so your ability to probe is moving higher and higher into the atmosphere. And so you're seeing radiation coming from higher levels of the atmosphere until you get into the core of the band, which is the highest opacity. And so it's showing you here that as you go, really high up in the atmosphere, you're actually seeing a temperature inversion. Things start to appear to come out in emission rather than absorption in this particular case. So the interesting thing is even just looking at the shape of that band, and say I could get 5 pixels across it, which was what I was going to ask for TPFI, we can tell quite a lot about what's going on in the atmosphere. It gives us a handle on the temperature pressure profile, and also tells us whether or not we have a UV absorber that's causing that temperature absorption. In this particular case, the UV absorber is sitting right there, which is ozone, but it acts as kind of a secondary confirmation of that. So here's some examples, and in fact, I did not put credits on this, and I'm sorry I missed that one, but this is Antigona Segura's work over here, Segura 2005, looking at the sort of ozone that we expect to build up in a terrestrial planetary atmosphere as a function of the incident radiation from different types of stars. And what we see is different ozone column depths, but the way those actually manifest in the spectrum of an Earth-like planet are based on not only the abundance of the ozone that builds up due to the UV spectrum of the star, but also the temperature structure itself, because that will affect, whether or not we're able to see this. And the particular takeaway from this is that for the K dwarf, we have a lower amount of ozone generated in the atmosphere, and it results in a more isothermal stratosphere. And so you get this characteristic U shape that's more like the Venus and Mars one. Whereas over here for the F star, you build up a super ozone layer, and then you end up with this massive temperature inversion, but also essentially the emission from that upper atmosphere starts to fill in the absorption itself as well. And you can see that for the ozone itself. So even though we have less ozone over here on the left for the K dwarf, and we have more zone over here for the case for the F dwarf planet, in fact, that F dwarf radiation is partly compensated for by emission, and so you're just not seeing as prominent a band. And so this is another lesson that you really do need to know the temperature pressure structure to be able to do accurate abundance determinations for things observed in the mid-infrared. So now I'm going to run through a few examples for Venus and Earth, and I will probably end up skipping Mars, and I apologize for that, but I only have a couple of slides on those anyway. So Venus, so I've said, in the visible, you have that largely reflective and scattering cloud that causes you not to be able to see down to the surface. But it was in fact part of my PhD thesis work to go and look at the so-called Venus near-infrared atmospheric windows. And so if you look at Venus in the near-infrared from about 1 to 2.5 microns, there is in fact radiation that escapes from the lower atmosphere, the subcloud atmosphere of the planet, and even as far down as the surface in these shorter wavelength windows. And you see this thermal emission most prominently on the night side of the planet. So if you look at the night side of Venus, you can actually see it, just like that 5 micron image for Jupiter, you can actually see it glow and have backlit cloud structures as radiation is coming out from the lower atmosphere. And so these windows occur between strong absorption from CO2 and water vapor. So where CO2 and water vapor don't absorb, you're able to get this emission escaping from the lower atmosphere of Venus. And it allows us to go after a whole bunch of different types of species, in this case, hydrogen fluoride, OCS, CO2, all those sorts of things, because we're able to now probe down into the lower atmosphere of Venus. And in particular, one of the things that we looked at was in these lower windows, the 1 micron, 1.1 micron window, we can actually see all the way to the surface, and we can see different thermal temperatures, different temperatures on the surface, denoting different different elevation structures on the surface. So shield volcanoes, the top of them, for example, are much cooler. And then in fact, there's a shield volcano over here you can start to see show up at about 1.1 microns. So maybe there's a hint of it at 1.8 over here. But this shield volcano, Beta Regio, and this is a model down the bottom, the bottom right-hand side here. But you can actually see the shield volcano and its cooler top be seen through these particular windows. These observations were taken from the ground with the Anglo-Australian telescope, but if we look within these windows, we're actually able to probe all the way down to the surface. Oh, and yeah, and I want to point out too that Mark made the aside that typically you have this transfer between reflectivity and emission, around about the sort of 2-3 micron region. But in the case of Venus, of course, because it's so hot at the surface, we're still emitting down near 1 micron. We're getting thermal radiation from there. This is also an example that, the atmospheric windows are going to end up being very important, especially if we're trying to get thermal observations of exoplanets. So here we're just showing an example of different types of compositions for a TRAPPIST-1b type planet. These are post-ocean loss, so we have high O2 atmospheres, high CO2 atmospheres modeled throughout here. And what I just want to show from this is first of all, this is the brightness temperature plot. Where basically the intensity or the flux, if you like, measured at a particular wavelength is then converted to the type of value that a black body would have. So you can determine the temperature of a black body that would emit that amount of radiation at that wavelength. So on this plot, a black body is a straight line. And so here's the equilibrium temperature for this object as the maximum equilibrium temperature, assuming 0 albedo for this black body. But you can see that this planet is clearly not, with these different compositions of black body. And I just want to point out that the windows in this particular case, the things where we see deeper in the atmosphere and so proceed at a higher temperature occur at different positions depending on the composition of the atmosphere. And so that's really important to remember that composition will control those windows. Okay, the other thing I want to point out for Venus is we can actually see things like air glow from the high upper atmosphere. We won't call them aurora because they're not constrained by magnetic fields, but they are, in this particular case, the O2 singlet delta air glow line from oxygen can in fact be seen in the upper atmosphere. The mesosphere of Venus can be used to actually track mesospheric dynamics up there. We can also use it to determine the temperature because the population of these lines within this particular band, if we can observe it at high enough resolution, can actually allow us to fit a temperature to it. And so being able to get air glow lines like that could potentially be quite useful. Over here, I'm also showing from oxygen. This is the oxygen green line, which is also be seen on Venus and might be the source of the ashen light, which people have talked about on Venus. So for Venus, we can do thermal, we can look at the clouds and reflectivity, and we can also look for aurora on the planet. And I know I need to wrap up here. So I just want to say, again, clouds and hazes can display strong features. This is for Earth. And so in reflectivity, this is what you would expect to see. In transmission, clouds, as I'm sure we all know, pretty much will truncate your signal when you look at terrestrial planets in transmission. And this is something we do have to worry about, again, for exoplanets as we look through that. So I just wanted to, point that out. For high altitude haze, like you would see on Venus, you get a very high truncation of the absorbing radius. And so you essentially cut off the depth of your absorption bands or your molecular features in that case. You can see haze scattering slopes even in the transmission. And again, these things can be modified by things like molecular absorption throughout here. So depending on which technique you use for looking at the planets, you're sensitive to more or less things. Clouds can also affect your emission, and they can essentially cause the planet to emit from a higher layer in the atmosphere where it is cooler, which subdues its radiation that's emitted, and that's what Mark was also showing for Jupiter. If you take the clouds away, you can get massive amounts of radiation pouring out from the hot lower atmosphere, and that's the case there. I might just skip over that one, but just to say that when you try and measure a disk average temperature for a planet, you are going to be thwarted by the fact that you have sight lines for an Earth-like planet with 50% cloud cover. You'll have sight lines down to the surface, but you'll also have sight lines just hitting the cloud and reflecting back up. in many cases, or just emitting from a cooler cloud above in the case of the emission plots here. And so what that means is you don't actually get the surface value. And for the Earth's disk average, in a disk average, you can only retrieve within about 12 to 16 Kelvin of the surface temperature. So we do need to take that into account as well. And then I just want to say that we can also look for life by looking at spectra of different terrestrial planets. Throughout the history of the Earth, we've had different atmospheres and different metabolisms being dominant, and there's a bunch of different things we can look for. Before oxygen has risen prominently, we might be able to see weak ozone over here in the ultraviolet. The hazes formed by methanogenesis might also be visible as a form of a biosignature and not just a haze feature. And then of course we have ozone and oxygen for the Earth. So I'm going to skip over Mars, sorry about Mars, and go to my conclusions. So my conclusions are planets are really not black bodies. That the planetary spectra are really sensitive to a bunch of different things that we can learn. But without the spatial resolution, if we don't have spatial resolution for exoplanet observations, then getting sort of an idea of what's going on at the surface is going to be problematic just because of the heterogeneity of what we're looking at. And the atmospheric windows may be present, but the location is strongly dependent on composition. And so when you go in to make your thermal phase curve measurements or whatever, take that into account when picking your wavelengths. And of course, I leave with one of my very favorite SKCD cartoons, which is kind of was my experience of the person saying, hey, isn't your field just pictures anyway? So, all right, I'll wrap it up there.
Thank you to both Vikki and Mark for 2 really great talks on solar system spectra. So we can open it up for questions now or discussion. So if you have questions, you can feel free to raise your hand or put your questions into the chat. If it's quiet, you can just go ahead and unmute yourself.
This is Debbie Reimer. I'm at Johns Hopkins APL. I have a question about when we look at the disk average spectra, for example, at Jupiter, I guess would be a prime candidate for this. Can you tell a difference between when we're looking just at Jupiter versus when we're looking at Jupiter with one of the moons in front of it, if all we had was a disk average spectra?
For Jupiter is so much bigger, the moons are not important, but you could imagine, say in an exoplanet case, if the moons got bigger, like you had a bright icy moon that was maybe Earth-sized, you'd worry, I think, about starting to fill in spectral features in Jupiter. Maybe you'd have to start worrying about looking for time-resolved changes in the spectra to try to tease that out. So I think it's not really a problem now, but it might be in the future.
Okay, thank you.
Mike Line has a question in the chat about Venus. In those atmospheric windows, the spectral windows, how do you know if you're seeing a surface or a cloud top that's near the surface?
Okay, yeah, so the answer is, Mike, we can cheat. And there's a bunch of things we could do because we know things about Venus. I was trying to get my presentation back up again, but I glossed over those. Remember, I showed you that only in some of those images that were taken at different wavelengths, you could see the surface, and others you could not. In the others that we could not, we were actually showing cloud opacity features. And so we're able to, in this particular case, we were able to actually map that dark spot to, a known feature on the surface of the planet. And to do that, I actually subtracted out the cloud features. So I was aware of where the clouds were and what their pattern was. And so I was able to actually discriminate those out. And so we do know we actually were looking at the surface. We also know that the H2SO4 clouds are in fact not very strongly absorbing throughout that wavelength. They still have a very high scattering optical depth, but their absorption optical depth is very small. And so we know that we're looking down through them in that particular case. And that scattering optical depth results in the footprint to see the surface of being only about sort of 50 kilometers. That's the best we can do spatially because of the scattering within the clouds. There's like a 30 optical depths of scattering in the cloud, but because the absorption opacity is low, we can still see all the way through. So we know that. Yes, I had a priori knowledge, but we also carefully went and measured them because we were exactly worried about that issue, about actually differences in cloud opacity fooling us into thinking we were seeing surface thermal differences.
Avi Mandel has a question probably for both of you. What would be the best strategies for breaking the radius albedo degeneracy for directly imaged planets?
I mean, that's certainly, I'll give a giant planet perspective. We've been thinking about that. And of course, I mean, as Avi well knows, that's a hard problem. One idea we've had is looking at as more partial phases, because as you go to more crescent phases, you tend to get scattering from higher in the atmosphere, more Rayleigh scattering and less absorption, or you're looking at scattering from hazes. And so getting some phase curve resolution can definitely help with that. And we, in the retrieval, seem to like that for nailing down the radius, but that will definitely be an issue. Again, a priori knowledge of the mass, relying on mass radius trends will help too. Vikki, do you have any?
Yeah, I think in our case, I mean, the real problem with terrestrial planets is the albedo could be pretty much anything from 0.06 all the way to 0.95, and so it doesn't really help. But what we might be able to do is, if we can get spectra of the objects, if we can identify aerosols or particular features where we can start to constrain the probability of what the albedo might be based on the composition and what we think is condensing out, so kind of bootstrapping our way up. That's one way we might be able to get at that. It doesn't help you if you're trying to use the radius to down select your targets, but if you've committed to actually observing them and you can take spectra of them, then we can start to learn about, oh, this thing looks like it has H2SO4 clouds. I'm going to propose an albedo of 0.6 to 0.8 or whatever, and try and constrain it in that particular way. But it is a big problem that we're going to have to deal with. But I think some compositional information might help us understand, the wavelengths we're observing, what kind of condensates we might have or what molecular absorption we might have going on.
And of course, I mean, as Nancy points out in the chat, if eventually if we got both thermal infrared measurements and optical measurements enough to start to nail down the bond albedo, 100 years from now, or when we have a fleet of spacecraft, you could start to solve for the radius like we do for asteroids.
Yeah.
But then, like for the giants, you don't know what the internal heat flow is, so it's still not a panacea.
Yeah. So in the mid-infrared for Earth, to riff off Nancy's point, the emissivities of the different types of surfaces are very similar. And so you don't have so much of the huge range of albedos that we can have in the visible. And so you can get away with that sort of thing. But yes, it does require a mid-infrared thermal measurement, which is not, that is a particularly challenging thing that we would need to have in addition to the visible. And maybe we can also get that from the ground. Maybe some of these M-dwarf targets might be crossover targets where we could potentially get an observation in the mid-infrared with these extremely large telescopes. So that would be really cool if we could get it like a Rosetta Stone object that was observed that way as
well. We have another question from Abigail Reimer on what would be some interesting measurements that you could do of the dark side of planets in the solar system, such as the ones that Cassini didn't do for Jupiter?
Well, what I was interested in is, the thermal emission. Is Jupiter emitting through the near-infrared windows the same way it does at 5 microns? Is there a deep enough in the hotspot regions to just try to isolate out what's the role of thermal emission versus reflection? But one thing Cassini did do, thanks to Bob West, is it stared at Jupiter from Saturn orbit, which is about a 65-degree phase angle, and watched Jupiter spin for one rotation period, which is great because that's a very similar kind of phase angle we would be getting for the directly imaged planets in reflected light in the future. And so that's a real good analog. And I think there's a fair bit of unpublished data from Cassini that hasn't come out on that yet. So any kind of places where we can get different phase angles, different wavelength ranges that we can get from the ground is interesting.
And we have another comment in the chat regarding sort of differences between aurora and air glow. And I guess I sort of had a related question to that for you, Vikki or Mark. What would be the observability of aurora for the giant planets or air glow for maybe more terrestrial planets for exoplanets.
Sorry, say that again. I was replying to Trump.
Have we estimated, or has somebody estimated sort of observability of something like the Venus O2 air glow or giant planet Aurorae for exoplanets?
Right. I mean, it's at least for the 1.27 micron air glow, that is most prominent on the night side, and so you just get swamped by, you know, the day side. Although interestingly, it has the same average surface distribution, same average surface brightness on both the day and night side. So you could potentially try and go after that. I know early in the field, back in the TPF SWIG days, we did discuss this, but I think it was basically considered impossible. And you do have to have fairly high resolution to be able to discriminate it from sort of the broader thermal in the window. So it's challenging, but yeah.
It might be a little bit easier with UV, like LUVOIR, if you picked LUVOIR. But again, you need higher spectral resolution. I think even LUVOIR, the UV wouldn't have high enough spectral resolution to see the UV feature. Lisa has posted a paper on Aurora on IMFORCE.
I think there were like 1 or 2 as far as I remember, but this is just one of the last ones on the M stars that came out in 2019, in case somebody's interested. And then we're trying to figure out whether or not, you know, how widespread they need to be for us to be able to see them at different wavelengths as a starting point. I'm sure they have references. I think they're like 3 or 4 papers on this. This might not be the most relevant one, but definitely a starting point.
Yeah, and I should also add there's discussion for Proxima Centauri B of potentially going after things like the green line in that case as well. But you do need high resolution.
We have a question from Federica. Federica, I'm sorry, I don't know what technique you're referring to here, but you say, do you think this technique applied to exoplanets could be a significant factor in improvement of the parameters of habitable zones?
Hi, sorry. I was thinking like when there was talk about like how you would assume albedo depending on even like very few informations from the atmosphere, since albedo is one of the big players in how we now define what a habitable zone is. Do you think going on and maybe getting a higher precision results from spectral measurement from exoplanets could change significantly, or maybe like improve the parameters we have for the calculation of boundaries of habitable zones?
Yeah, so obviously any information you can get on the planet that you're trying to model, I think it's maybe not so much on the limits of the habitable zone, which sort of are defined for a canonical type of planet, but trying to figure out whether the planet you're looking at fits where that fits as far as the climate and the surface conditions. Yeah, it's going to be really important to potentially understand if there is a reflecting or scattering cloud there, because that will impact the climate. And to understand what absorption is there as well, which will also impact the climate. So the habitable zone is really defined for sort of an Earth-like planet that has a carbonate silicate cycle that allows it to up its CO2 as it moves out in the habitable zone region. And it's not defined for the huge diversity of planets that we're likely to see. And so for those planets, we will need to go in and survey as many greenhouse gases as we can, figure out the reflectivity, all of that sort of thing, to help us try and assess whether the surface of the planet, is able to support liquid water. So that'll be a really important part of the characterization of terrestrial planets for habitability.
Okay, and then we have one more question in the chat from Akash Gupta regarding different types of clouds and aerosols, and what can we say about their albedos and compositions from spectra?
Well, I say for the giants, certainly there are spectral features. A lot of them tend to get washed out if you have a wide particle size distribution. But sometimes, for example, for Jupiter, people have identified ammonia, the ammonia and possible water clouds even, but it's very tricky. And I think certainly from the near-term exoplanet perspective, it'll be a challenge. I don't know what Vikki thinks about that for the terrestrials.
Yeah, no, I mean, and I skipped over Mars, and this is my punishment for that. But yeah, so on Mars, for example, you can see strong features from silicates when dust is lofted into the atmosphere. So that's one sort of spectral discriminant we have for that. But also, yeah, cirrus ice clouds on the Earth have a very strong absorption feature around about 1.5 to 1.6 microns. And so that could also potentially help us say, oh, I'm looking at a water cloud or an water ice cloud or whatever, and help us to constrain the albedo. There are, I believe, H2SO4 features. I can't remember exactly where they are. And also, and it was a backup slide on my presentation, there are techniques where we can actually use polarization, the phase dependence of polarization, to look at rainbows that can effectively help us discern what kind of a scatterer we're looking at. And so should we ever get a telescope with that capability, we could go look at phase dependence in the scattering and be able to pull out composition from that as well. So that's another thing we could potentially go after.
Are there any other questions before we finish up? You're right at about noon. If not, let's give Vikki and Mark a virtual round of applause. Thank you guys for your wonderful talks today. And I think, Vikki, this recording will be posted on the Nexus site that you posted a link to.
I'm still holding out that we'll get it on the ExoPAG SIG site at some point, but for the moment, it's going up on the Nexus site, and I can probably get that posted in the next few hours. I'll try and get it up there. So, okay.
Perfect. Okay. Thank you, everybody.
Thank you, Laura. Thank you.
Yeah, thanks, Laura, for hosting.